So there are some problems that computers are relatively good at doing today, right? Basic math formulas, this number times this number. Even my watch can do that right now, right? You put that in the calculator, you put it in a computer. Our computers, our classical computers, which we have today, are pretty good at coming up with this number. We have the algorithms, we have the processing speed to do that. However, if you make one little change and you ask for the opposite, say, what are the two integers that make up, when multiplied this, or integer factorization? Well, that's a lot harder for a computer to do. And then when you add more numbers, let's say you added some more numbers out here, right? The longer, the more difficult. You need a much more powerful computer. So our modern classical computers will struggle with these kind of problems. Thus, the need for something different, the need for quantum computing. In this video, we'll have just a brief basic introduction to the ideas that are foundational to quantum computing and think about some of the things that might be coming in our future. Let's get started. So I mentioned classical computer or traditional computing. Let's compare traditional to the idea of quantum computer. So classical computers or traditional computers, they work by a stream of electrical impulses, which you know as bits, 0, 1, right? A binary system. So this is the classical method. We have a bit, which is a 0 or 1, and it's just everything from pictures to text is really just a stream of these electrical impulses, which are interpreted as zeros or ones. So when you're watching this video today, it was recorded using bits. Now you may know bits, you put a few of them together, you get a byte, and then you put millions of those together, you get a megabyte, gigabytes, terabytes. That all comes from the information at the basic foundation, which was all about bits. Now, what do we know about bits? They're either 0 or 1, meaning it's sort of like a switch. It's a 0 or 1, a 0 or 1, 0 or 1. There's nothing in between. There's nothing off to the side in a different dimension. It's just 0 or 1. And that's how our classical computers have worked for us and actually done pretty amazing things. Now, what about quantum? Well, quantum computing doesn't use a bit. It uses a quantum bit or a qubit. What's different about a qubit? Well, a qubit can be in different states at a time other than just zeros and one, okay? So quantum computing uses qubits, can be many states at a time. Now, this is actually one of the very first quantum computers that we have. Kind of looks like something from, I don't know, Doctor Who, some crazy fantasy show. I'm going to go over qubits and how they work, but the basic point I want to bring out to you is that classical computers, we got a 0 or 1. Quantum computers use qubits, which we have many different states other than just 0 and 1. Okay, so what is quantum computing? Quantum computing is an area of computer science that uses quantum theory. Okay, well, what is quantum theory? Okay, quantum theory is just how we look at the behavior of energy, that should be an E, sorry about that, energy and matter at subatomic levels, right? So we're looking at electrons, we're looking at photons, we're looking at protons, we're looking at energy within those. That's all quantum. Think smaller than an atom, subatomic. Okay, so how can electrons, photons, protons, how can all of these things help us in computing? Well, we actually have this idea of using qubits. Because they exist in multidimensional states, we can use a lot more information when we look at a quantum wave function. Okay, so think back to your high school chemistry or physics class. We often talked about these subatomic particles existing in sort of waves, or as a function in a wave. So you may have remembered something like this, right? A quantum wave function, so how a particle is actually acting. This is often how we represent some of these particles, and how they're interacting. Now, this is a little difficult to deal with and for some people to visualize. So if you study quantum computing a bit, you'll see often people use a visualization of this quantum wave function. And what we're visualizing here is really, if we're picking two distinct states, a 0 and a 1, right? 0, 1. This quantum wave function could be up at a 0, it could be down at a 1, or it could actually be somewhere in between, right? So when we visualize these, we often draw a little arrow, right? Saying in this case, oh, it's closer to 0 than it is to 1. Now, what we know is that quantum states are always in a state of movement, right? So this is always moving around. But if we take a snapshot at a certain moment in time, it should be more in one direction than another, right? So when we're showing a wave, these can get complicated. But if you think, okay, I'm looking at my qubit here, right? This is just a visualization of a quantum bit. Wherever the arrow is pointing, that means we're closer to one end than another. And we've arbitrarily picked zeros and ones here because that's a little easier to understand. Now, how does all this work? Well, to understand how this can apply to quantum computing, we have to understand a feature of quantum theory or of quantum phenomenon called superposition. And this is what I was sort of explaining. If we have a wave function, a quantum wave function, which is closer to 0, we would say this is maybe in the 0 state. In this case, it's clearly in the 1 state. But if we were to take a snapshot in time and it was sort of here, this is a superposition, right? It's some combination of 0 and 1. It's neither fully 0, it's neither fully 1. Now, there's a probability in this case, as you can see, that it's a little closer to 0, but still it's in a superposition state. Okay, what does this mean? This means we can now calculate a probability of the state of a certain qubit if we take a snapshot at a certain moment in time. So, once again, if you got this qubit, and right, remember, it's a wave function. It's moving all around, moving all around, moving around. If we take a snapshot, if we measure, and we're not taking a literal photo, right? We're using circuits and we're taking a measurement at a certain time. And we said, okay, in this case, notice that the wave function is leaning towards 0. So it's more likely a 75% chance of being 0. Well, what about this one? Probably closer to an 80% chance of being 1. You see how this arrow is pointing closer to 1 than it is to 0. Well, there's also a moment where there's a 50-50 chance of it being a 0 or 1, right? This is not as helpful. These are more helpful when calculating probability of a state. Okay, so this is called superpositioning. When we have a particular qubit that has some position in between 0 and 1 for the example we're using. Another really important feature of quantum computing that you have to understand is entanglement. Entanglement is the idea of qubits being linked together, okay? Or entangled together. So let's start by reminding ourselves of classical computing, right? Bits are independent, 0 or 1, 0 or 1. This bit, 0 is different than this bit, 0 is different than this bit. They are independent, they are not linked together, they are not entangled. That's our classical computing. But when we look at quantum, what we know is that these qubits actually can be entangled together, linked together. So now, instead of just zeros and ones, where we have a binary system, this one can be 0 or 1, this one can be 0 or 1. So when you put the two together, now you have 4 options. And I show that here on a probability table. So for example, in this case, kind of looks like we're probably going to get a 0 and probably going to get a 1. The probability of that, right, might be a certain time. But you could also get a 1 and a 1, a 1 and a 0 and a 1, 0 and a 0. So there are now the 4 options instead of the 2. Okay, so a few more features of quantum computing that we want to talk about. Interference. And for when we talk about interference, I want you to think about waves, okay? So maybe think of a sound wave. Constructive interference increases the probability of a correct answer in quantum computing. All right, so Herder, what is constructive interference? All right, think of some ways. Here's a wave. If we were to take this wave and add it to this wave, right? You've got a little amplitude there that goes up. You got the amplitude there. Oh, those are the same. So if I added this amplitude to that amplitude, notice I got a higher amplitude. Same thing. We go below the line here a bit, go below the line here. If I add these 2 below, now notice that I've got a bigger this plus this gives us this. So this is constructive interference. And when we're adding these waves, this increases our probability of getting a certain answer because of this interference. Now the opposite, destructive interference, will decrease our probability. So for example, if we're measuring a qubit, a wave, right, a qubit wave, and we take this one plus look at its inverse. Notice here we went up, here right away we went down. Here we went down, here we went up. If you take those and overlay them together, notice that these cancel out, these cancel out, these cancel out, so we're left with sort of just a straight line. This is destructive interference. The reason this is important is because if waves are canceling each other out, those are probably incorrect. We want constructive interference to increase our probability of getting certain correct answers when we do a measurement. All right, so interference helps then with probability distribution. So if I'm using a 3-qubit system, right? 1, 2, 3. Think about it. Basically, instead of just a 0 and a 1 option for an output, now I've got 8 different ones, right? Because if you take these together, I could have a 0, 0, 0, 0, 0, 1, 0, 1, 0, 0. We have all these different choices when we now have 3-qubit system. So when we add all these probabilities together, we now have a closer idea of what we think the correct answer will be. So once again, why is this perhaps going to revolutionize things? Because these qubits are much more, theoretically, are able to handle much more data because we're not just listening or we're not just using a binary system, we're essentially using an exponential system. And that leads me to this slide. Why so much faster? These computers can do things. They've already shown it, the ones that are sort of the beta programs that we see from Microsoft, IBM, Google. They are showing us that they can already calculate things at speeds that traditional computers just can't even touch for years and years and years. So why is this faster? As I mentioned, because of exponential growth. Because qubits can be entangled together, right? Remember bits, 0 and 1, can't be intertangled with classical computing. But with quantum qubits, we can entangle many, many together. So our possible number of states increases exponentially. Here's a little formula basically that kind of shows that. If I'm looking at 2 qubits, remember I've got 4 choices. It could be a 0, a 0, a 0, or a 1, a 1 and a 1, or a 1 and a 0. Those are 4 choices. But now imagine if I had 3. Then I go up to 8 different states. 4, go up to 16. You can see how this exponentially grows, where if we're having a 6 or 8 qubit computer, we've got 64 possible outcomes of data. And this is going to really allow much more processing. Okay. So how does this work? What are the learning processes? Well, we're still going to use algorithms in quantum computing. So you may remember from a previous video, an algorithm is just a rule that tells a computer step-by-step instructions on how to complete a task. So algorithms for some problems are pretty easy. That's why we have classical computers. But for some of the bigger problems, like that one I led with, that integer factorization that I led the video with, we need more advanced computers. IT security, right? If you think of hackers trying to hack into our systems, we need really fast quantum processing to be able to thwart those attempts. Or if you are a hacker, a quantum computer would help you get into some place that you wanted. So let me give you an example. This is actually the first problem that scientists really showed was able to be much better with a quantum computing. And it's the Deutsch-Joyce problem algorithm, where they insert a Boolean function, f, and we want either a 0 or a 1 in return, right? So we write this formula. Here's the classical algorithm for it, where we're really wanting a 0 or a 1 in return, right? It might lean towards 0. You might get a bunch of zeros. You might get a bunch of 1s. But you also might get 50% zeros and 1s. Now, this actually is pretty slow with a classical algorithm computer. But when we actually use a quantum algorithm, and I know these look scary, we're really just using these gates and then taking a measurement, okay? So I've been using lots of words here, algorithms, gates, etc. Let's dive into that a bit. A logic gate is how computer circuits basically help us to find out some information, right? So classical computing even uses gates to build a circuit. So for example, we have NOT gates and NOR gates. What's that mean? Well, if you've ever taken any computing or computer science, a NOR gate means something would process only if A nor B are 0, right? So if A and B are 0 instead of 1s, then we get an output of this to process. That's a NOR gate. A NOT gate is an inverter table. So if we inputted a 0, then we want an output that's not 0, which would give us a 1. So if you put a bunch of these little gates together, that's how we've built circuits over time. Now, quantum computing uses quantum logic gates as a building block, right? So here's our typical little circuit that we might put on a semiconductor like some silicon, right? A, B, and then we get some outputs here. Now, in quantum, these operation changes the qubit between states. So what a gate actually does in quantum computing is change the qubit states. So here we have 3 different sort of qubits that we're looking at. Those are the 3 qubits. Then what we got to do is we got to initialize or reset them all. Then we're going to put some gates in that are going to change the state of the qubit. Then we're going to measure that using some either classically controlled or quantum and get some output, okay? So if you aren't familiar with computer science, this is probably way beyond what you were ready for in this video. But I think the point is still there, that we can still use logic gates just like we do in classical computing in the world of quantum computing. Okay, so I showed you a picture of a quantum computer earlier, but like what is it? Like a quantum computer, what's the physical stuff? Is it circuits? Is it wires? Like what is it? Okay, so there's 2 big ones that I want to go over. The first one that's currently the most popular is a superconducting quantum computer. Basically, they use superconducting wires with a break, which you'll see here is actually a Josephson junction on a chip, right? So these superconducting qubits are really functioning as sort of artificial atoms, or we call them quantum dots. And we have 2 states, either a grounded state or an excited state. So here's a prime example. Here's a Josephson junction. C is a layer of insulator. A and B are superconducting, right? Now, they don't have equivalent wave functions, right? So they're in different quantum states. And then what we have is the ability to then measure the output and see if we are ground or excited. Here's what one of those actually looks like that was made. The other idea is a quantum dot quantum computer, and it actually uses physical electrons. So it's using a physical entity, actual electrons, right? Just like we use in electricity, actual electrons, or they can use photons, and they put it on this semiconducting chip. All right, so here's my electron spin. So my electron spinning, and we can measure electron spin or charge. And what we'll find is that once these receive, right, some information, it might receive a little zap here, these will spin, and then we can measure it. The measuring of this will give us the probability of certain answers, okay? So what is a quantum computer? Well, it's made of these chips, right? But the chips are different. Some of them have these superconducting wires, some of them have these electron dots, and then we're going to measure spin. All right, so a lot of this is theory, but some of it is putting into practical use. So I want to just show you a few things that we already know are happening. Google has been working on this. Google AI has been working on quantum computers for a long time. And their goal is to complete Sycamore by 2029. They spent billions of dollars on this. So they have a beta version of Sycamore that's already out, that's doing some amazing things, but they're really putting a lot of money in this. IBM, same thing. Here's actually that picture I showed you earlier from IBM. And they're wanting a 1,000 qubit quantum computing by the end of 23. That's a pretty lofty goal. We'll see how it goes. Microsoft, too, of course, their quantum platform is the Azure platform. So you can see the big three names are working on this. They're putting a lot of money into it. That really tells us that, you know, if these three big are putting into it, we're probably going to see some major developments going on. All right, to wrap it up, what are some potential applications? What can we actually do this for? Why would we have quantum computers? Well, one really important thing in science is the modeling of subatomic particles. You probably remember something like this from a chemistry class, right? Protons, neutrons in the center, you got your electrons, but it's really hard to model all of that, right? So with quantum computers, with these super fast processing, we'll be able to model this and understand really what's happening at a quantum level. Also, molecular interactions. If you have this chemical and this molecule and this chemical and put them together, how are they going to interact and predict it, right? So instead of actually going to the lab and seeing what happens, we can run a simulation to see what goes on. Climate change, super complicated. We need these massive supercomputers to model what we think for our weather. But with quantum states, we will be able to predict and model climate change happening much, much easier. And finally, as I mentioned earlier, cybersecurity. This is why the banks, this is why some of these big companies are really investing, because we need to secure our cyberspace from within and from attackers outside as well, right? So this was a video that had a lot of information in it. Hopefully you picked up one or two things. To me, if there's a takeaway, it's bits versus qubits. Here, 0 and 1. Here, many states because of the ability to entangle them. Therefore, much greater computing